what we want to do is expand on that and explain exactly what's the big deal about this bridge. Why is this truly a better world than these other ones to begin with? So let me start off with this idea, multiplying. If we wanted to multiply a couple complex numbers written in standard form, these happen to be binomials, before Euler, here's what probably you would do. You would start to FOIL this and you'd say, alright, 3 times 1, that's 3, and then 2i plus 1, that's 2i, plus 6i plus 4i squared. The I squared becomes negative 1, so that's 3 plus 8i plus a negative 4. That becomes a total of negative 1 plus 8i. That's how you would do it before. Now we have a second option. Euler says, hey, we've got a much better idea. Here we've got an elegant way to do it. What you do is you cross this bridge over to Happy Land and you say, you know what, we're going to write these as Euler numbers. And to write these numbers as Euler numbers, keep in mind you find the r and the theta. This is 3, this is 2, so this would be equal to, I think we've done this before, it would be the square root of 13, the square root of 13 e to the I, and what is the, I need a tan inverse. This is not a famous angle, so I need to find the tan inverse. Let's do that. The little magic number machine. Tan inverse of 2/3, that's 33.7, so that's 33.7 degrees approximately, times 1 plus 2i. To find that one, you go 1 over 2, so this will be the square root of 5, and then tan inverse of 2 over 1. So I'm going to clear all this, and I'm going to do tan inverse. The opposite is 2, adjacent is 1, so the ratio is, let's do it correctly, 2 over 1, just so you see how we calculated that, 63.4. So this would be, so for this one right here, the angle is 63.4 degrees, and the r is equal to the square root of 5. So therefore this would be the square root of 5 e to the I times 63.4 degrees. So over here, Euler would say, hey, to multiply these, all you do is multiply the coefficients together, so it would be the square root of 5 times 13, that's 65, times e raised to the, how do you multiply numbers that have the same base? Well, when you multiply numbers that have the same base, all you do is add the exponents. So this would be 97.1 degrees. That's how you would do it in Euler world. Okay? And this is a non-famous example. For famous examples, it works just as nicely. Try a famous example. Alright, let's try some famous ones. This is a famous one because the angle, I know if you go over to the right 1/2 and up square root of 3 over 2, that's a famous triangle. This is 1/2 square root of 3 over 2. So this must be 60 degrees. R is equal to 1 in this case. So that's why I'm calling these famous. This one over here would be a similar one, but for 30 degrees. The opposite is 1/2, the adjacent one square root of 3 over 2, and that's 1. So anyways, here's how multiplying works. In the regular world, in the mundane world, you would start foiling this. You'd say 1/2 times that would be the square root of 3 over 4, plus the insides would be 3 over 4i, plus the outsides would be 1/4 I, plus the last ones, that would be square root of 3 over 4i squared. Now the I squared becomes negative 1, square root of 3 over 4, that becomes negative square root of 3 over 4, and a positive 1. These guys go, and that leaves you with 3/4 I plus 1/4 I for a total of 1i. Right? In the Euler world, says Euler, take this bridge, come with me to the Euler world. This one becomes e to the 60 degrees I times e to the 30 degrees I. And to multiply these two numbers, whenever you've multiplied two numbers that have the same base, all you do is add the exponents. And so 30i's plus 60i's which is 30 i's plus 60 i's. I'll let you use your calculator on that one. That's 90 i's. And so this was how Euler would do it. Incidentally, we use the Euler identity. This one, e to the I theta. If you have e to the I 90 degrees, that becomes cosine 90 degrees plus I sine of 90 degrees. And what does that become? Cosine 90 degrees, that becomes, here's the cosine graph. Cosine of that is 0. Plus I 90 degrees, that becomes 1 I. So this becomes a total of I. And so this becomes, famous one right here, this becomes 0 plus I times 1, which is equal to I as expected. I just did this part to double check what was expected. You see that? Nice. Multiplying in this world is a bunch of foiling stuff. Multiplying in this world is just adding exponents. That's why it's so nice. It gets even better than that. Try dividing now. Now suppose you wanted to divide. Let's just say we wanted to divide this number by that number. If you were doing the old style, you would multiply top and bottom by the conjugate. You would go 3 plus 2i over 1 plus 2i is the same as that times 3 that times 1 minus 2i multiplied on top and 1 minus 2i multiplied on the bottom, and so on and so forth. Euler has different ideas. Euler says if you want to divide two numbers, if they're monomials, and you have, especially if parts of it have the same base, various exponents, all you do is subtract the exponents. So Euler would say this is just the square root of 13 over 5. 13 over 5 times e, and then you would subtract the exponent. So 33.7, take away 63.4. That's 33.7 minus 63.4. That's approximately 29.7 degrees negative. That's it. As easy as it sounds, that's all you got to do for Euler. So this would be square root of 13 over 5 times cosine of negative 29.7 degrees plus I times sine of negative 29.7 degrees. And you can calculate those if you want. This seems like a fun exercise. Calculate this whole thing and distribute that, and you should get exactly the same answer as doing it this way. I'll let you work on that. Incidentally, a lot of people abbreviate this cosine of the angle plus I times the angle. Often people will abbreviate it like this. Just so you know, often people will abbreviate like this: CIS theta, which means cosine of the angle plus I sine of the angle. This is just short for this whole thing. Just so you know, everybody does. Some people do it. Anyways, dividing non-famous numbers. There's totally different flavor. Here you got to do conjugate stuff. Here just subtracting the exponent, just like that. Let's do another dividing one, but this time let's do some famous ones. So this one, again, if you were to divide that but divided by that, you'd have to multiply top and bottom by the conjugate. You'd have to go 1 over 2 plus the square root of 3 over 2i divided by the square root of 3 over 2 plus 1/2 I, multiply top and bottom by the conjugate on the bottom. So you'd go square root of 3 over 2 minus 1/2 I, square root of 3 over 2 minus 1/2 I, and then clean it up, and you'd get the right answer. Euler proposes a different idea. If you've got e to some angle and e to some angle and they're being divided, all you do is subtract them. So 60 i's take away 30 i's, that becomes 30 i's. And that's it. You're done. In Euler world, you're done. Dividing monomials is really easy. Dividing numbers that are written with the same base is really easy. In the Euler world, all you do is subtract the exponents. So you subtract the bottom exponent from the top. And you could convert back again using the identity. You could say this is cosine of 30 degrees plus I sine of 30 degrees and compute that, and that would take you back to the regular world standard form. Okay? But wait, there's more. I should make an infomercial on Euler identity. Not only can you multiply and divide in a much easier way, but wait, there's more. Imagine taking the power of this complex number written in standard form. On a regular day, you would probably have to try to do something like this: 3 plus 2i, and then maybe square that. I don't know. You'd have to do that times itself 10 times. So there's many ways to do it. You could square it and then do that 5 times, or you'd have to expand that using the binomial expansion theorem, or you'd have to do it one by one where you FOIL it. Anyways, no matter how you look at it, it doesn't look like a particularly fun problem to do or elegant. This looks like a lot of grunt work. Euler proposes something much more elegant. Euler says, hey, this is much easier. In the Euler world, here's what you would do. You would change this to the Euler form, which we agreed was the square root of 13 times e to the I think it was 33.7 degrees. If not, don't worry about it. Just let that slide. It's close enough. Euler proposes, hey, this is a different kind of problem than this one. This is a binomial, so to take that to 10th, you have to expand that and FOIL. Here, this is a monomial. To take that to the 10th, it's a million times easier. All you do is take the square root of 3 to the 10th power times e to the I. This is power to power. This would be 337 degrees. And you're done. This would be 13 to the 5th power, following your algebra rules, because this is 13 to the half times 10 is 5, times a cosine of 337 degrees plus I times sine of 337 degrees. And that would take you back to the other world. And you're done. Just like that. This is amazingly elegant. You take the 10th power of this. So easy. Over here, it's a totally different world. Okay? I told you. Euler's big. Big time. He was a real deal. Okay? And you can even do it on some famous ones. Let's take this one, for example. The 10th power. This is the one where you go over 1/2 and up square root of 3 over 2. So this is the medium one, famous one. This is 60 degrees. And this is 1. So therefore this is equal to, Euler would say this is equal to e to the 60 degrees times I. And raising it to the 10th over here is a piece of cake. E to the 600 degrees I. And that's a piece of cake. That's cosine of 600 degrees plus I times sine of 600 degrees. I told you. If you compute that, that will take you back to the standard world. Okay? Here, I'll compute it this for fun. If you go all the way around, that's 300. If you go all the way around, that's 360 plus 360. That's 720. Well, we gone too much. If you go 720, we got to go back, take away 120. So this would take away 120. That would put you 60 short. The reference triangle would look like this. This is 1. This is 60 degrees. So this is 30 degrees. So this is 1/2 square root of 3 over 2. Negative, negative. So cosine would be negative 1/2 minus square root of 3 over 2 I. That's what it would equal to. I told you. With great elegance, take it to the 10th power. No problem. But wait, there's more. Let's run down through my infomercial cheat sheet here. Multiplying, easy. Dividing, easy. Powers, easy. How about roots? What does Euler's identity tell us about roots? Well, let me tell you. Take, for example, this number, the square root of I. Have you ever wondered what is the number that when you square it, you get I? And you might think, hey, maybe that number is I itself. But wait, if I square I get negative 1. So that doesn't help. Then you think, hey, maybe this negative 1. But when you square it, you get 1. So that doesn't help. You want something that when you square it, you get I. What is the number that when you square it, you get I? This is a difficult problem in this world. In the world of monomials, even if it's a complex number, it's a difficult problem. How do you figure out the square root of negative I? But if we just cross the bridge and come over to the promised land, to Euler land, becomes a piece of cake. Let me tell you what I mean by that. For roots, here it is. I can be written as, you can either do the old-fashioned way, or you can just imagine it on the complex graph. What is the angle here? If it's a famous one like this one, I can figure out it's 90 degrees, and this r is equal to 1, so it's equal to 1 times e 90 degrees I. Right? Stop me if I'm lying. This is the regular world, monomial world. This is Euler world, exponents powers of e. Regular world, Euler world. Now, over here, the Euler world is hard, but over here, e to the 90 degrees I, oh, it's a piece of cake. This is just the square root of that. So you could take e to the 90 degrees I and raise that to the 1/2. Distribute that, that becomes e to the 45 degrees I. Stop me if I'm lying, which becomes cosine of 45 degrees plus I times sine of 45 degrees. I can't slow down. This becomes the square root of 2 over 2 plus I times the square root of 2 over 2. I know those because they're famous. And there you go. The square root of I is square root of 2 over 2 plus I square root of 2 over 2. If you don't believe me, try it. Here's what would be the ultimate test. If you take the square root of 2 over 2 plus square root of 2 over 2I, and you square it, you should get, well, you could get some stuff and simplify, but ultimately you should get I. Try it. If you follow this, you get the square root of 2 over 2 squared plus 2 times the square root of 2 over 2 times the square root of 2 over 2I plus the square root of 2 over 2I quantity squared. That's just foiling that. First one, last one, the 2 times the inner ones. This becomes 2 over 4. This becomes, well, I can cancel those. That becomes 2 over 2I. And this becomes 2 over 4I squared. But wait a minute, what is I squared? I squared is negative 1, so this becomes 2 over 4 plus I, that's 2 over 2 is 1. I squared is negative 1, so it becomes negative 2 over 4. Oh no, we didn't. 2 over 4, negative 2 over 4, that's gone. I told you. See why they pay me? Told you. A number that when we square it, you get I. Not only that, but you know, there's more. You could easily find the cubic root of I. In this world, it might be hard, but if you think about it this way, 90 degrees I, do you know how easy it is to find the third power of that? All you do is multiply the powers, and you're done. So, again, let's go back to our little thing here. What is the Euler's identity good for? It makes multiplying totally easy, dividing a piece of cake, powers a piece of cake. It helps us find roots that we never even hoped to find before. But wait, there's more. Let me tell you the fundamental theorem of algebra story. Okay? Fundamental theorem of algebra. The fundamental theorem of algebra tells you basically, if you've got a polynomial equation, such as this one, 3x squared plus 5x plus 7 is equal to 0. This is a polynomial equation of degree 2. The number of solutions is equal to the degree. This is degree 2, so there are exactly 2 solutions to this polynomial equation. It generalizes that. It says if the polynomial equation was degree 3, there would be exactly 3 solutions. If it was degree 4, there would be exactly 4 solutions, and so on and so forth. Super famous fundamental theorem of algebra. Gauss proved it. Gauss, as they call him the Prince of Mathematics. That was his PhD thesis at the age of 17. Anyways, this is not Gauss's party, so I'll let that slide. But Gauss proved the fundamental theorem of algebra. The degree of the equation is equal to the number of solutions. So let's see what would Euler say about that. Okay, what does Euler's identity say about that? Well, apparently at first it seems like nothing, but then you start to dig into it and you start to see some amazing patterns. Let's see if we can see those amazing patterns. This equation, x equals 1, What's the degree for that equation? The degree is 1. Therefore, fundamental theorem of algebra would say that has one solution. What is it? Well, you're looking at it. X equals 1. That was easy. What about x squared is equal to 1? What's the degree for that equation? Degree 2. According to the fundamental theorem of algebra, how many solutions should it have? 2. Where are they? Well, you could say x squared minus 1 is equal to 0. Then you could say x minus 1 times x plus 1 is equal to 0. Therefore, x equals 1 or x equals negative 1. So there are your two solutions. I told you, two solutions, degree 2 equation. No problem there. What about degree 3? X to the third is equal to 1. Degree 3. Degree 3. According to the fundamental theorem of algebra, how many solutions do you have for this equation? You have exactly 3 solutions. What are they? Well, you could find them this way. X to the third minus 1 is equal to 0. Therefore, x minus 1 times x squared plus x plus 1 is equal to 0. This is a famous factorization, by the way. Difference of cubes. You should all know how to factor that. If not, may I recommend MathHands, the algebra version? Alright, you should know how to do this, and then you got something times something equals 0, so x minus 1 is equal to 0, x squared plus x plus 1 is equal to 0. So this one you could solve easily, x equals 1. This one you could solve easily by using quadratic formula. Negative 1 plus or minus the square root of negative 3 all over 2. I know I did that really fast. Sorry, I can't help it. X equals negative 1 plus or minus I times the square root of 3 all over 2. There you go. Count the solutions. How many solutions do you see here? 1, 2, and 3. You got 2 of them here. 1 for the plus and 1 for the minus. So you got 2 of them here, 1 here, a total of 3 solutions. What was the degree here? 3. I told you. That's why they pay me insane amounts of money. Degree 3 means 3 solutions. Degree 4, x to the fourth is equal to 1. According to the fundamental theorem of algebra, how many solutions would you expect? You would expect exactly 4 solutions. What are they? Well, fortunately, you've got the skills to solve them already. X squared minus 1 times x squared plus 1 is equal to 0. X minus 1 times x plus 1 times x squared plus 1 is equal to 0. Therefore, x equals 1, x equals negative 1, x squared plus 1 is equal to 0. So x squared is equal to negative 1. So x equals plus or minus I. How many solutions have you got here? 1, 2, 3, 4. 4 solutions. I told you. It's a nice pattern, huh? And so on and so forth. Now, apparently, this still doesn't tell you exactly my point. I haven't told you the punchline yet. Exactly, you know, what does that have to do with the beautiful, the most powerful, most elegant identity that humans have ever created? Not humans, only the man that could calculate this like others breathe. My buddy Euler. What is the connection between this and the fundamental theorem of algebra and their roots of unity? These are all called roots of unity. These are the fourth roots of unity. These are the cubic roots of unity. These are the squared roots of unity, etc. What's the connection? Well, here's the connection. The connection still doesn't seem apparent, but you start to get at it when you start to plot these excuse me, on the complex plane. Let me start to plot these. For x equals 1, here is the solution. No. Hold on. Can't rush perfection. X to the third is equal to 1. X to the fourth is equal to 1. Now I'm going to leave some space here to see if you guys can guess the x to the 5 is equal to 1. Huh. Alright, what were the solutions for x squared equals 1? Just x equals 1. Where can you plot that? Well, you could plot that right around here. There's the x equals 1 solution. X equals 1. Check. Can you see the pattern yet? No, of course not. How about for this one? where are the solutions for this? The solutions were 1 and -1. Remember? You remember 1 and -1. Those were the solutions for that one. Where are they on the graph? Well, one is here, 1, and the other one's there, -1. Can you see the pattern? Say no. How about x to the third? What are the solutions for x to the third? They were 1, -1/2 plus 1/2 square root of 3i, or -1/2 minus I square root of 3 over 2. Where are they on the complex plane? Well, here's 1. The other one was -1/2 and square root of 3 over 2i. That would be somewhere over here. -1/2 plus the square root of 3 over 2i. The other one was -1/2 minus -1/2 minus square root of 3 over 2i. That's the other one. Can you see the pattern yet? Maybe, maybe not. In fact, the pattern becomes much more clear if you put these on a unit circle. There's the one circle. There's this circle cut in half into 2 pieces. Here's this circle cut into how many pieces? No. Oh no, we didn't. Well, yes, we did. We cut it up into 3 equal pieces, 120 degrees apart. This one, oh no, what were the solutions for this one? I, -I, 1, and -1. Where are they on the graph? 1, -1, I, -I. Whoa, no, we didn't. Where are the solutions here? The solutions occur on the unit circle, equally spaced, cut into 4 pieces. Boom, boom, boom. Those are the 4 solutions. This one was unit circle cut into 3 pieces. This one was the unit circle cut into 2 pieces. This one was the unit circle uncut, just left as 1 piece. Do you see the pattern now? How do you like me now, huh? I told you. But wait, there's more. If it was x to the 5th is equal to 1, and you were asked to find all the roots of this polynomial, which are called the 5th roots of unity, and you had to guess based on this pattern, and you just had to take a wild guess, how would you begin to guess? You guessed it correctly. The first one would be at 1. The other ones would be equally spaced around the unit circle, 360 degrees. If you can eat 5 spaces equally spaced, each one comes out to 72 degrees. So the first one, the next one would be at 72 degrees. So this would be EI to the 72 degrees, which you could also write as cosine 72 degrees plus I sine of 72 degrees. Next one would be right here at I 144 degrees, E to that. Next one would be that plus 72 degrees. The next one would be there plus 72 degrees. Next one would be back here, which will repeat it up to 360. And there you'd have your 5 roots of unity equally spaced on the unit circle. Isn't that amazing? I thought it was amazing. 210, 216. Next one would be that plus 72. That would be 288. 288 degrees I, where that's the power of E. And then this one will get you back to 360. So which is the same thing as 0 degrees. So you wouldn't get anything new, you'd get the same roots. That's the pretty amazing pattern for the roots of unity. But wait, there's more. What does that have to do with Euler's identity? With the man that could calculate like others breathe? Well, you might be wondering, okay, that's nice, a pattern, but where does it come from? It comes from exactly Euler's identity. Let me take this one, for example, and break it down using Euler's identity. To help you see, this will shed some light into the issue, I think. If suppose you wanted to find x to the 4th is equal to 1, and you had no idea what it is, and you say, you know what, I have no clue what x is. X, I don't know. Who knows? Je ne sais quoi. You say to yourself, you know what, I don't know what x is, but I know whatever x is, I can write it as e to the I theta. Assume you know that the r is 1, because it has to be a root of unity. Just let that slide for now. Or So then we substitute this in here and we say, all right, e to the I theta to the fourth power is equal to 1. And not only that, but the 1 can also be written in the Euler world. Let's move everything in the Euler world. 1 is the same thing as e to the 0 degrees. Right? It actually, more than that, it could be e to the 360 degrees. You agree? Or it could even be e to the 720 degrees. In fact, it could be e to the any multiple of 360 degrees. Yes? So I could rewrite this as e to the I fourth theta is equal to e to the any multiple of 360 degrees, any integer multiple of 360 degrees. How is it that, times I forgot the I. Sorry. How is it that this e raised to this power can be the same as this e raised to that power? How? Well, for sure they would be the same if these were equal to each other. If 4 theta I is equal to k 360 I, then this would be true, then that would be true, then that would be true, then that would be true. So this would mean that if I solve for theta, theta is equal to, cross out the i's, any multiple of 360 degrees divided by 4. So theta is equal to any multiple of 90 degrees. So this is telling me that if theta is any multiple of 90 degrees, x will satisfy this equation. So that means x is equal to e I, my theta here, I'll substitute it in here, k times 90 degrees. That would mean that that would mean that, for example, if you take k equals 0, that means e to the 0 I, comma, if you take k equals 1, e to the I 90 degrees, comma, e to the k is equal to 2, e to the I 180 degrees, and e to the I 270 degrees, and e to the 360, but then it repeats itself. There you go. I found 4 solutions to the equation, and the fundamental theorem of algebra says that's all there is. There aren't any more. So this is a way to shed light into exactly why the roots of unity occur in this really nice pattern. Here, I'll say it a different way. Let's try the one for the fifth. X to the 5 is equal to 1. This one is a sort of a down and dirty way of doing it, but I'll do it anyways. So again, you could play this game. You could say 1 is equal to e to any multiple of 360 degrees, right? And then suppose this is not always legal, and you'll have to think about why it is or isn't legal here. But suppose you could take the fifth root of both of these exponents. Okay? Again, this step is very delicate. You shouldn't just try it at home whenever you feel like it, unless you feel like being a rebel. This step is you shouldn't do it unless you got supervision close to you. Anyways, you take the fifth power, and that would give you that x is equal to e k any multiple of 72 degrees. I forgot my I. And there you go. For all various values of k, if k is equal to 0, you get x is equal to e to the 0 I. If k is equal to 1, you get x is equal to e to the 72 degrees I. If k is equal to 2, you get x is equal to e to the 144 degrees I. I told you, and so on and so forth. Didn't I tell you? This is another way of viewing exactly why the roots of unity always occur in this nice pattern. So the fundamental theorem of algebra is connected to Euler's super famous identity, cosine theta plus I sine theta is equal to EI theta. Okay? Okay, where was I? That was nice, huh? The roots of unity, super famous roots of unity. Fundamental theorem of algebra by Gauss. Alright, I thought we could finish off today with one of my favorite proofs of all times. Do you guys remember the mother of them all? It tells you how to add, how to do cosine of x plus y is equal to blah 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 blah. Oh no, I think it was minus. The mother of them all, super famous. This is the tomato plant for all other identities. This is where everything comes from. And we proved it. We proved it by taking a triangle and letting it fall. It was all about letting it fall like this. And that was a really nice proof. Now though, I'm going to show you that was really a blue collar proof. A pick and shovel proof. Euler, my buddy here, has got the most elegant proof of all times. This is the white collar proof. This is the opera, go to opera and fine wine and dining proof. The other one was a cheeseburger proof. You guys want to see it? The mother of them all. The question is, what is cosine of x minus y? Whoa. Cosine of x minus y, what is that equal to? That's the question. And what in the world does that have to do with Euler's identity? Can you believe it? Doesn't seem connected, huh? I'm telling you, math is one of the most creative endeavors in the world. Let me prove it for you. Okay, so I'm going to prove this one, the mother of them all. It's the mother of them all because from it comes all the other identities that, for example, double angle identities, power reduction identities, sums to powers, etc., etc. Double angle identities. This is the mother of them all. We've already proven it this way, but by letting a triangle fall. But today I wanted to prove it using the famous Euler's identity. And just keep in mind, you don't have to watch this. In fact, I don't have to do this. Sometimes, dancers, they dance for money. And sometimes dancers just dance because they love to dance. Math teachers are the same way. Sometimes we prove things just for the paycheck, just for the money. And sometimes we prove things just for the love of proving things. So I'm just telling you off the bat, this one is not for the money. This is just because I love this proof so much. This one's on the house. Alright? So in order to prove that, here's what we need: a couple ingredients. First ingredient that we need, of course, is Euler's identity. Okay, we've already learned that. We already practiced it a lot. I'm going to put a little check mark on that. No, I'm going to put a little yellow check mark on that. Foil, this is from algebra. First, outer, inner. I'm going to put a check mark on that. Really, the only other ingredient that we need is something that I called the guessing game. So let's learn that one. It'll take us about 20 seconds to learn the guessing game. I won't even tell you what the rules are. We'll just start playing it. The guessing game goes like this. I write a complex number like 3 plus 5i. And I tell you it's equal to some other number. It's equal to blank plus blank I. And in that blank I put x and k. And I try to ask you, can you guess? That's why this is called the guessing game. The guessing game. Can you guess what x is? And can you guess what k is? Assuming these are real numbers, here's the way the guessing game goes. If you have a complex number that's equal to some other complex number and they're both written in standard form, then the real parts have to be equal and the complex parts have to be equal. So therefore, here's a good guess for you. X would have to be equal to the real part 3, and the one that's next to the y, the one that's next to the I would have to be the imaginary part. That would be the k. It has to be equal to the 5. That's how the guessing game goes. You get it? It's pretty easy, huh? Let's try it again. Let's try it again. Let's clone this guy. But then let's make this stuff disappear. And let's clone this one so we can try it again. And so I've got the guessing game again here. Suppose I had 3 halves I plus 4 is equal to a hair plus a chair I. Ooh, take that. Can you guess what the hair is equal to? And can you guess what the chair is equal to? Let me tell you how the guessing game goes. You assume that they're written in standard form, so then this part, which doesn't have an I, must be equal to this part, which doesn't have an I. So the hair must be equal to the 4, just like that. And the imaginary part, which is the share in the I, must be equal to the imaginary part here. So, therefore, the h must be equal to 3/2. That's how the guessing game goes. So, hair is equal to 4, h is equal to 3/2. You get it? I think you could use one more. Let's play the guessing game here. Suppose you had 4 plus the square root of 3 times I is equal to no, plus the square root of 3 plus 7 times no. Sorry, I'm getting nervous all of a sudden. Plus 1 over the square root of 2 is equal to a plus a bi. Can you guess what the a is, and can you guess what the b is? It's just called the guessing game. Assuming a and b are real numbers, and these are complex numbers written in standard form, which piece goes with which? The a. Just think about it. The a, does it have an a? No. You've got two pieces here. This one has an I and this one has an I. The a does not have an I, so therefore the a must match up with this one. And so the b, which is the imaginary coefficient, must match up with that. So therefore you can conclude that, here's the conclusion, your a is equal to 1 plus the square root of 2, and your b is equal to 4 plus the square root of 3. You get it? That's called the guessing game. Pretty easy, huh? Alright, I'll stop there. These are the three ingredients. Euler's identity, check. FOIL, check. The guessing game, check. Okay, two complex numbers are equal if and only if their corresponding real parts are equal and the corresponding imaginary parts are equal. That's it. That's all you need to prove the famous mother of them all. Can you believe it? Amazing, huh? I'm gonna do it. I'm not gonna do it for the money. This is just for the love of proving things. Watch this. In fact, I never told you guys this before, but you know that sheet with the famous identities? I don't have any of them memorized. Not even the mother of them all. Every time I need to remember it, all I do is prove it using Euler. Let me tell you how it goes. This is what I do. Every time I gotta remember that, I go like this. E to the x. What would Euler say about e to the x I? Well, Euler would say that that's equal to cosine x plus I times sine x, right? What would Euler say about e to the negative I y? Well, the negative can go as a coefficient, as it can go with a y, so it would say that this is equal to cosine of negative y plus I sine of negative y. Yes or no? Stop me if I'm lying. That's exactly what Euler's identity would say. In fact, you could clean this one up. It would say that this is, what's cosine of a negative angle? Cosine doesn't care if the angles are positive or negatives because cosine is an even function. Sine does, so that the negative could come right through the sine function, and that would give you that much. Right? Still though, that doesn't tell you anything. But wait, there's more. What would happen if you multiply the left sides? These two. Well, you'd get something like this. E to the xi times e to the I times negative y. And on the right hand side, you multiply these. So you'd have cosine x plus I sine x times cosine y minus I sine y. Is that right? Here, I'll show you what I did. I multiply this one and this one. That's that one and that one. And on the right hand side, I multiply that one and that one. That's those two right there. And I'm multiplying in the regular mundane world, and I'm also multiplying in Euler's utopia world. And they have to be equal because they're the same numbers, just written in different ways. Written in the regular world and written in the Euler world. But wait, there's more. How do you multiply numbers that have the same base but different exponents? You add them together. So this would be e. That would be e that's not blue. That would be yellow e. E to the I times x minus y. Because you would just add the exponents, x plus a negative y. On the other hand, we know how to do FOIL, right? You're not afraid to do FOIL on this, are you? No, you're not afraid. This is a paper tiger. Cosine times cosine. This would be cosine x times cosine y. That's the first. Outer would be minus I sine y cosine x plus the inner. That would be I sine x cosine y. That's the inner cosine y sine x. I. Then the last ones would be minus I square sine x sine y. Is that right? Whoa. Let me see. Actually, this cleans up nicely. But wait, there's more. This cleans up nicely because I square is negative 1. So negative 1 negative times negative, this would be a positive. So this means that e to the I x minus y is equal to cosine x cosine y plus sine x sine y. That's this piece added with that piece. That's this whole piece. I still got to do these other ones over here, the ones that have i's. So I'm just going to factor out the I, and I'll say this is plus I times, and I'll put parentheses here, sine y cosine x plus sine x cosine y. Stop me if I'm lying. No, I'm not. But wait, it gets better than that. This guy is equal to that guy is equal to, what is this equal to? What would Euler say about this number right here? Euler would say that this number is equal to, let me just rewrite it. So I don't have any room there. But I don't want to go to the next page because that wouldn't be pretty. This is just enough room for us to fit it in there perfect. It's like a beautiful dish. You only want to use one dish, not two dishes. Alright, so this guy, what would Euler say about this this one? Euler would say this is equal to cosine of x minus y plus I times sine of x minus y. Is that right? That's what Euler would say about this one. Now, my friends, look at this part right here. I'm going to circle it because it's so crucial. We're basically done. This little box thing is so crucial. Because, remember, what were the ingredients that we need? We used Euler's identity, we used FOIL, and now we need to apply the guessing game. You guys remember what the guessing game was, right? What was the guessing game? If this complex number is equal to that complex number, can you guess how they match up? How the pieces match up? You remember that, right? So let's look at it. This right here is the number on the left. This is the number on the right. It's got pieces. It's got a real piece and an imaginary piece. This one's got a real piece and an imaginary piece as well. This piece right here, this is the real piece. It must match up with the real piece there. Stop me if I'm lying. Stop me if I'm lying, please. Cosine of x minus y is equal to that. And this piece right here must match up with that piece right there. So what does that tell you? That tells you that necessarily cosine of x minus y must be equal to the real piece here. Cosine of x, cosine of y, plus sine of x, sine of y. That's why they pay me insane amounts of money. We've proved it. This proves exactly what we wanted to prove. Not only that, but it proves more. It proves that sine of x minus y is equal to that. So it proves two identities with one stroke. Genius. Brilliant. Okay? I love this one. What can I say? Let the music say it.